All right, lesson 3, building quadratic functions from geometric patterns. It's a cool down called a quadratic function. Sometimes a quadratic relationship can be expressed without using a squared term. So far we've looked at like n squared or t squared or x squared. Sometimes we can write it without that squared term. So let's take a look at this pattern of squares, for example. If you take a look at this and see how this is growing, well, we start off with, let me put in some numbers here. We're starting off with 2. Let me make that bigger. We're starting off with 2, and then we've got 6, and then we've got 12. So we're adding 4 here, and we're adding 6 here. So we can see this isn't linear. It's not exponential either, because to get from 2 to 6, you'd multiply by 3. And if you multiply by 3 again, you wouldn't get 12. So it's not an adding pattern. It's not linear. It's not a multiplying pattern, not exponential. This is, in fact, quadratic. Now, if you noticed, I was able to pretty quickly come up with how many squares are in each of these diagrams. I didn't actually count every single square because I didn't need to. I know how to multiply. If I take a look at this step 1, this is 1 by 2. This is 2 by 3. This is 3 by 4. And if I were to go over to step 4, I can pretty clearly see that there's a pattern here. 1, 2, 3, step 1, step 2, step 3, 2, 3, 4. Well, step 1, that's 1 more. Step 2, that's 1 more. Step 3, that's 1 more. So step 4, I could just draw this. I could say that's going to be 4 by 5. Now the question is, what happens over here at step n? I don't know exactly how big this thing's going to be, but if I look at the relationship between the step numbers and this side length, I see it's the same thing. So step 1, 1, step 2, 2, step 3, 3, step 4, 4, step n, n. Step 1, 1 more than that. Step 2, 1 more than that. Step 3, 1 more than that. Step 4, 1 more than that. Step n, 1 more than n. So if I were to come up with the number of squares over here, well, this was 3 times, let me make that a different color. This was 3 times 4. This was 2 times 3. This would be 4 times 5. This would be n times n plus 1. And if you remember the distributive property, you'll recall that you can actually simplify this and multiply that out, and you would get n squared plus n. So we started with an expression that didn't have a squared term in it, but once we figured out the pattern and came up with an expression to figure out the number of squares, we could simplify it, and we could see that our equation does in fact still come out to be quadratic. So that's one way to do it. The other way to do it, and this is kind of interesting actually, we have a 1 by 1 plus an extra 1. We have a 2 by 2 plus an extra 2. We have a 3 by 3 with an extra 3. So if I go all the way out to n, I would have an n by n with an extra n, or n squared plus n. So there's a lot of different ways that we can divide up these diagrams and look at the number of squares and come up with an equation to tell us the number of squares in our particular pattern. Now, real quick here, quadratic function. If you'll recall, function notation, f of n equals n squared plus n. Remember, the way that a function works is like a machine in a factory. If this is f of n, n is my input into here, and what my function machine will do is it'll take the step number, it'll do stuff to it, and in this case, it'll take the input squared plus another input, and we will get out the number of squares. That's all function notation means. So this f of n, this is not f times n. We're just saying f is the name of the function, n is the input, and this is what our function does. You put n's in, you get number of squares out. So, for example, if we've got f of 2, that's not f times 2. That just means I'm going to take my input of 2, and I'm going to take that input squared plus that input itself again. So 2 squared is 4, plus 2 is 6. So for an input of 2 into my function machine, I'm putting 2 into here. I'm taking my function machine and doing the stuff to it, and out on the other end, I get a 6. So let's take a look at this. Here is a pattern of squares. You saw 2 different ways that I looked at the same set of squares and came up with an expression for the number of squares. I want you to do the same thing. Think about how you could quickly add up the number of squares in step 4, maybe, or even step 5. What would step 10 look like? And then take that all the way out and think about, well, step n. What would you have for step n? If it helps, draw it out for step 4 and 5, count up some numbers, and think about these shapes and their sizes and how you could possibly write in a function or an expression. Is the relationship a quadratic function? Explain how you know. If you have any questions, let me know.